In this lesson, we're going to talk about the second derivative. Remember that a derivative itself is a function, so if we can calculate the derivative of a function, we could calculate the derivative of the derivative. Now there are some actual reasons for this that we'll talk about in this lesson. So the second derivative of a function, we will often denote by f double prime of x. That's how we read this, f double prime of x. It's equal to the derivative of the derivative. Another notation you may encounter is this d squared y over dx squared. It's kind of like you take the d over dx and you square it, but we didn't bother with the parentheses for this particular notation. So then the question lies, what would it mean if the second derivative were positive or negative? This concept is a little bit tricky, so we'll see if we can make some sense of it. Remember that when a function has its derivative positive, that function is increasing. Now this is a bit of a stretch for some of our minds. It can be a tricky concept. But if we say that the second derivative is the derivative of the derivative, that means that the second derivative is the derivative of f prime. So if it's the derivative of f prime, and that function is positive, that means that f prime would be increasing. Similarly, that would also say that if f double prime were negative, the derivative of f prime being f double prime that's negative, that would say f prime were decreasing. Now let's go back and think for a second. F prime of x is the rate of change. Remember when a function had its rate of change increasing, we had a term for that. We actually called it concave up. So when the derivative is increasing, the rate of change of the function is increasing, which means the function is concave up. Similarly, if the derivative function is decreasing, then the function is concave down. Now, all of this information can be a little bit tricky, but the one context that's the easiest to keep together is that if the second derivative is positive, the function is concave up. If the second derivative is negative, the function is concave down. That's one great reason to talk about the second derivative because it helps us to talk about the concavity of a function. Let's try to put this together in a handy table. If a function is positive, remember the geometric interpretation of that would be the function lies completely above the x-axis in that area. Similarly, if the function is negative, it lies below the x-axis. What we've talked about so far is if the derivative is positive, we knew that the function was increasing. If the derivative was negative, we knew the function was decreasing. Now that's actually not the area I'm working in, but let's put that in the table. So now what? What can I say about the derivative or the second derivative when we just know that the function is positive or negative? Well, the actual answer is nothing. And similarly, if the derivative is positive or negative, we don't know anything about his derivative, which would be f double prime. And in the last two rows, we can actually use what we had on the last chart. If the function is concave up, we get that the first derivative is increasing and the second derivative is positive. Similarly, the second derivative would be negative and the first derivative would be decreasing if the function were concave down. Now let's talk about the intervals on which the second derivative is positive and negative based on what we remember when we talked about concavity. For the first one, remember that we can look at concavity by drawing these secant lines. And notice that all these secant lines lie above the curve. That says that it's concave up everywhere, so the second derivative is concave up everywhere. The way we will write that is f double prime of x is positive on negative infinity to infinity, and f double prime of x is negative nowhere. Now let's look at the next example. Notice if I draw a few secant lines, they appear to be below the curve each time. That would say this is concave down everywhere. Consequently, f double prime of x is positive nowhere, and f double prime of x is negative on negative infinity to infinity. And then for the final one, this one actually has a little bit of concave down and a little bit of concave up. If we were to draw in some of these secant lines, we'll notice that before 0 it appears to be concave down. And then when we draw things to the right of 0, it appears to be concave up. So at 0, there is a spot where the concavity changes. Now when I write down my answer, I'm not going to put a bracket in my intervals. I'll always use parentheses just like I have in the past. F double prime of x would be positive on 0 to infinity, and f double prime of x would be negative on negative infinity to 0. Let's talk about the second derivative from a table approach also. This table gives the number of abortions reported in the US in the year T. What we'll do is calculate some average rates of change just between the number of years. And we're going to pretend those average rates of change are close enough to the derivative, and that'll help us figure out a little bit about what the second derivative does. For the first one, 1972 to 1975, we're going to do 1034 minus 587 over, I'll just do 75 minus 72, though putting in the full year is technically what we need to do. I get 149, and I'll put that in right here for my delta A over delta T. And then we'll do 1975 to 1980. For that one, we have 1,554 minus 1,034, and again, I'll just put 80 minus 75. When I do this one, I get 104 for my average rate of change. We'll fill in the rest of the chart similarly. Notice that because I'm stopping at the 2000 to 2005, the way that I'm doing this, I will not have any data for the last cell. Now let's consider the differences, because the second derivative is a lot like the second differences. So if I just look at how they're changing over time, that will give me a little bit of an idea of the second derivative. Notice that we have some changes in sign. It's going to negative, 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 but then it hits positive and back to negative. Let's write what's going on. From 1972 to 1990, the abortions were increasing in total, but they were increasing at a decreasing rate. So now let's take a look at 1990 to 1995. Notice that we started with 1972 to 1990, where everything was increasing. And then from 1990 to 1995, suddenly things started decreasing rapidly. But then from 1995 to 2000, it started decreasing a little bit less rapidly. And then from 2000 to 2005, it started decreasing more rapidly. So let's just write an overall statement for what was going on. From 1990 to 2005, abortions decreased quickly, slowed down, and then sped back up. And you can see this in the data here. You've got this concave down, which is actually talking about the year 1990 to 1995. And then 1995 to 2000, it was suddenly having a positive, but it was still decreasing. That concave up is a slowing of the decrease. And then we had a speed up of the decrease.